So it's really a great pleasure to be here again. I was actually a SAMC fellow 10 or 15 years ago, and most of the questions here, I think, were still questions then. Or does it work the other way around? I'm not sure. So this work really wouldn't have been possible without a large number of the people at CATS, and you'll see them references as the slides go by, and at the end. They also wouldn't be possible without, it draws a lot from Ralph's book, and from a paper, writing a paper with Jim is a very enlightening experience. But there's a paper which hopefully will appear this year, which many of the results are drawn from as well. The large yellow bar are things that I really wanted to talk about, but due to the talks this morning, I put in more slides, and they're to try to get me to take slides out. I mean, hopefully you can read the title, so if you really like that, you can ask during the question time, or anytime later this afternoon. But this is actually from the SAMC, from the webpage, from the MUMS webpage. And this idea that mathematical models intended for computational simulation and complex real-world processes. So that's great. I agree with many of the goals, but this idea of two communities, I think somehow there's a bit of a third community of practitioners, right? I mean, the people who actually are more interested in the phenomenon. So we've seen examples, but I'm going to show a lot more. And this question of how you actually make what we're talking about, how do you see that it works? How do you use it? What do you do when it doesn't do what you would expect? I'm interested in uncertainty of the model itself, but I'm not actually sure I can quantify it. I would really like to. I've been trying to for a long time, since I was here 15 years ago. But the idea of quantifying the uncertainty in predictions when you go to do it, well, it's easy to do. It's just when you look at what actually happens, it doesn't always reflect what you said was the uncertainty in the predictions. So what do we do in those cases, right? We can keep fine-tuning and making the method better and showing that it works not only for Gaussian observational noise, but skewed observational noise, but it's not working in practice. So I'm going to try and start a little bit more at the other end and hammer some of the ways it's not working in practice and what we do. Determining unknown parameters. So, you know, there's this Paul Teller wrote a very nice paper called The End of the Perfect Model, where he talks about how statisticians and physicists and a lot of scientists have this idea. So actually, Chatfield says something similar. So we're searching for the perfect model, and when we get to the perfect model, everything else will be okay because all of our tools work in the perfect model land. I sort of think I won't be here when we get there, so if anyone gets there. But what I would like to do is sort of, okay, so it doesn't work. What do we do now? What do we do now? He suggests giving up on the perfect model for the good of science. So this idea, what does that mean? Well, in part that means that these unknown parameters, it's not that they're imprecisely known, it's that they're indefinite. There is not a number which goes into the equation which gives us the right equation. No such number exists. They might be good for this or good for that. But there's not really a question of determining what those numbers are. How do we cut that? Reducing the complexity of a model. So all of my operational guys would be happy to reduce the complexity of the model, but it always makes things so much worse that they just think it's a silly idea. So that's a pretty hard sell, unless you can show that for their problem, it's actually going to let them do more. Right. Determining the best among competing models, or alternatively, I don't know what that word is, utilizing all the available models. I think this is great, utilizing all the available models. I actually want to breed them in action. But we really need to think about what we mean by best. And once we leave the perfect model, once we are actually dealing with models which are structurally corrupt, then there isn't a best. We have to think more about the best for this question or for that question. And that makes things, again, much more interesting, but also different than this sort of doing the math carefully. Finding the most influential components, I've got no objection to that, it's a good idea. And developing methods for model criticism. I think this is great. I don't know where I've been. I've been looking for model criticism all the time. And I would love to hear more model criticism where people don't yell at you. Except it's not going to necessarily be the model. And then uncertainty and linking different models together. I'm going to show a number of examples. Again, in the longer blurb, it talked about the way that, that you do empirical-based models. For me, these are applied maths or statistics. And you use simulation models where you write down the equations you want to solve first and then try to match them up to the thing you're trying to solve them on. And in practice, in weather forecasting and climate work, they're always merged together, right? So I think this question of thinking about that more carefully would be very good. So what is UQ? I just want the blue part, the end-to-end study of the reliability of scientific inferences. And end-to-end means going all the way down to counting the number of reindeer in Utenheimen, right? So where are the reindeer? There haven't been enough reindeer here. We have a lot in the middle, sort of like lots of tools. It's sort of like you're wandering around in the store with all the American store, not British store, with all these beautiful selections of fantastic woodworking tools and steelworking tools, but you don't actually have an idea what you want to build yet. So what should you buy? And you can make, that's I feel that way a lot, right? Oh, okay. And it doesn't really say too much about, right? This doesn't really have to be mathematical, I don't think. But the other thing I want to do is I want to divide UQ problems and tasks generally into two different kinds. Weather-like tasks, which has weather-like UQ, and climate-like tasks, or climate-like UQ. So weather-like tasks with the model, this is pretty easy. The model lasts a long time relative to the forecasts. You may be making 4 forecasts a day, like in weather forecasts, and the model sort of lasts 2 to 6 years, depending on what you count as a change in the model. So we have a huge forecast outcome archive, right? You use the model a lot. You can learn about the model. A climate-like situation is one in which the model lasts much less than the lead time of the forecast. You're trying to forecast 100 years ahead, and you change models every 5 or 6 years, right? The forecast lead time is longer than you last. So neither the model nor you are going to learn from those long-range mistakes. You can learn lots of stuff. But the way you need to, I believe we need to think about UQ differently in these two situations. So here are the reindeer. Here are a couple of examples from this year at LSE. So the first one is we partnered with the START network. This is a set of NGOs which try to do anticipatory disaster risk reduction. What they want to do is they want to get supplies on the ground before the rains turn all the airfields into mud, right? They want to try to act before disasters happen. And they successfully authorized payment to get things happening in Pakistan a few months ago before a major heat wave hit, and they're very happy with this result. And there are just many, many different pieces to make this whole thing work together, and we need to understand where the models have information and where they don't. Probably the most valuable thing we do with START is we tell them when to ignore weather models. When the weather model, they have 72 hours to decide, I send money or I don't. And they can they're doing it in a probabilistic way. They don't mind sending money when nothing happens. But if they do it too much, they run out of money before the end of the year. Okay? Reindeer. So a question for reindeer people is things like, if you're in Norway, how many reindeer hunting licenses should I issue in January? And this is one that really mixes together models which really are doing population dynamics in a purely statistical way, and weather forecasting models. And we didn't really get information on that, but one of the things that we managed to pull out was what they actually needed to measure instead. We learned enough about the way reindeer do things and the way the models were acting to know that it doesn't really matter if it's cold or if it's hot, the sort of variables they were using. What matters if it gets colder than hot and then colder than hot, because reindeer eat lichen on rocks. And as long as there's a lot of snow, they can push it away. As long as there's no snow, they don't need to push it away. But if it freezes and then unfreezes and freezes again, it's ice and they can't get to the food and the little ones die. The last one is actually experiment that I've been working on for a long time. This is actually, it's about almost life-size up there. It's a rotating fluid annulus. You'll see it a couple of times. It's cold in the middle and heated on the outside. And there's lots of fluid dynamics work done studying what's happening inside that annulus. And this happens in two different ways. Sometimes it's done by large simulation models, and sometimes it's done by empirical models. One of the problems we have is people almost never compare these two. The idea of getting them to actually work together would be even better. And then we have the Earth. So, is that blob in the Gulf going to turn into a hurricane or not in the next 48 hours? So we'll talk about that a number of times. Unfortunately, there are no blobs anywhere in the Atlantic Basin this morning, but you'll see that picture. And then one more. There's a sense in which the annulus was created by the Met Office in the late 50s, 60s as a model for the Earth. So I'm not sure if UQ wants to go there, but there are many cases where we actually have models where, like a mouse, right? The mouse is a model for us. And this issue of the uncertainty in going from analog models which are done by analogs. Okay? So those are the questions there. The last question is the perfect model and plausible deniability. You'll also find that there are some people who really want an answer, and they don't necessarily have a perfect model answer, but they need to do something, and they need to put somebody else's name by the number that goes into the form. And this attempt to maintain plausible deniability, right, theirs. It's your fault if you give them the wrong number. And this, I think, one of the reasons they don't really like PDFs. Okay? But this is from this morning. I mean, this is really the point. The central goal of computer modeling is to evaluate the quantity of interest. I mean, several people said that already today also. I might say the question of interest. But in my experience, very, very often, the code is written before the question of interest is even thought about. It's like going in and buying all those tools to build I don't know, I'll just use them, right? So how do we sort of put the practitioners, well, I think this is why we don't have as good contact with many of the practitioners as we could, because they go off and do it their own way. So here's the traditional approach to forecasting. What I want, oh, there it is. There's the light. Okay, so this is time, and this is x in the Lorentz equations, a third-order chaotic dynamical system, probably chaotic. And what we have here is we have the probability of x in this little circle, conditioned on the observations over some period in the past, and the dynamical system, knowing the perfect dynamical system. So you notice they're actually not filling the space or on some attractor of the system. So we sample from that, and we run those forward, and this is a PDF running forward in time. It should go into the future. So it does cool things. It does things no linear system can do. Like, you see it goes down and it gets sharper again. It's easier to forecast this system out here at 0.42 than it was at 0.2. And once we see this, we can go back and understand it analytically. It does other things that are sort of worrying to people who don't tend to evaluate PDFs, but tend to evaluate point forecasts or use any RMS-styled error measure. So it comes down, goes up, comes down, goes up. It splits, changes color. What's the change in color? Well, the color is the standard deviation. If it goes through black, the standard deviation is larger than the invariant measure, than the natural prior, which means that under linear measures, it has no information. But as you see, it has a lot of information. What's worse is, here we're basically symmetric. So an RMS measure would say that the best forecast would be right there. And that's clearly not what we want to be telling people. In the Lorentz model, this is sort of strong winds from the left, strong winds from the right, and the best RMS forecast. If we try to tune our parameters, the parameter it wants is the one that says there is no wind. Okay, so why do we do this? Well, first of all, it's sort of cool. It now takes up 1/3 the computing budget of the entire weather forecasting enterprise. Right? They had a party when they beat data assimilation and the high-res run and using more computer time. This actually does impact the way the things happen. But predictability is different for different systems. For a given system, predictability is different on different days. So here we have an ensemble of the blue blob, an ensemble of the green blob, and an ensemble of the red blob. Right? And this was work done by Dew at Durham. And then we let them go. See, like the red one's already stretched out. This idea that the predictability time is 2 days, this is nonsense. First of all, it only applies to infinitesimally small perturbations. As long as the error is infinitesimal, I don't care how big it gets. Secondly, it really doesn't reflect the nature and complexity of the different distributions. So the idea of ensembles started in 1992, both here in Europe, in weather forecasting, was to try and capture this variability and the uncertainty in the forecast. But there's a difference. These are two ensembles with exactly the same initial conditions, one under a system, which is the Lorentz equation, and the other is under a model, which is very much like the Lorentz equations. All I've done on the right-hand side is of the ODE, I've separated c times the sine of x over c. So when sine of y, when y is small, is y, right? So sine of x over c goes to x over c as c gets big. C times x over c goes to c. But for any value of c, I destroy the structure of the attractor. And that means that my initial conditions would be picked differently in the two different cases. And so here, I don't really think we have a chance for getting actionable on probabilities that we could bet on, probabilities that we would want to act on. Right? But on the other hand, it can shadow the system sometimes for quite a long time. So there's lots of information. One of my questions is, how do we get that information? And this is a reason why we're going to have these problems. It's a question of structural stability of equations in dimension more than 2 for big nonlinear models, any nonlinear model. Okay? But it's simply it's really a nasty situation. We might actually want to be sampling from the attractor of the system, but these little gray points in the back are supposed to be the points on the attractor of the model as a cartoon. In fact, the system might not even have any point. The attractor might not even have, the model might not even have any points in this region. This is much, much worse than chaos. Chaos is just a question of monitoring the uncertainty in a couple of reals, which are the parameters, and a couple more reals, which are the individual initial conditions. Right? This is functional structural error. And it would be great for someone during this program to tell us how to get over it. Poincaré was upset. Poincaré became heavily depressed. He made a similar discovery. And at Smale, I can't quite tell, but it seems that I can't find it documented. I think he also just became depressed when he realized that the results he had proved in 2 dimensions, not only could he not prove them, but they didn't hold higher. So let's get back to operational modeling. This is a picture from your book. It's from several places. But when we want to model, what we do is we sit down at a computer and start doing stuff, and then we realize we can't, and then we have to read some books. So I'm going to ignore this kind of problem. I tried to scan your book, and it didn't like it. So if something really horrible happens, bugs, mistakes, sabotage, is huge ones for cybersecurity, I'm ignoring those for the moment, and I'm just going to ask whether or not we can actually quantify the uncertainty using this model. And my argument at the end is going to be we can't. We have to come out of model land in order to quantify the uncertainty of this model. As long as we're working inside model land, we can't get there. So what we have is we start off with Navier-Stokes equations, nice partial differential equations, boundary conditions in physics. We immediately take the PDEs and turn them into ODEs because we can't do continuous space. We take the ODEs and turn them into difference equations because we can't do continuous time. We take the difference equations, we turn them into a cell-to-cell map because we digitize the reals. And we end up with this assembler, right? This assembler runs on this IBM 3, I don't know if this machine still exists, but on this IBM 360. It's 360 assembler. If we take the same Fortran code and change the parameter values or change it to a different machine, if it's a climate model, it probably won't work. And it works, and it compiles, right? The answers are different, significantly different, and I'll show you why. So rarely, if ever, is operational UQ going to actually be able to work only with the details of the model? The model is that, right? And I don't want to work with that anymore, although it's pretty fun. But that's not all. So, the world isn't Navier-Stokes. And it turns out that our initial conditions, initial conditions aren't on that grid. Initial conditions are analog temperature measurements. And the boundary conditions, we know are not reasonable. So this is what if you take the real-world boundary conditions as measured from a satellite, altitude, and you subtract off Hadesium-3's altitude in the climate model, this is what you see. And this red stuff, that's a 2-kilometer wall of rock. That's not in the climate model. It's not that we don't know how to simulate rock. It's that we can't afford to simulate rock. That means that the errors you see in climate models, if they're sort of due to things like this, you're not going to find them by looking at climate models. Any climate model. This, maybe this is now 1 kilometer in the next thing. These are known neglecteds. There are many things, right, that we actually know are important, that we know have an impact, but we ignore them. We put them aside. And sometimes we do it for very good reasons. The model wouldn't run fast enough. And other times, Well, other times we could actually figure out, well, what happens if these really were higher? How long would it take before it changed something in the Amazon? And then how long would that take before it fed back other places? Can we somehow put would how long could this model potentially be interesting? So here are the two models for the annulus. This is coming back to this issue of parameters. So the parameters in a simulation model, this is work by Roland Young at Oxford. He's actually simulating expansions of the fluid flow inside this annulus, this perfect annulus, right? It's truncated equations, but this annulus has bumps. Occasionally, somebody accidentally trips over the cord. You know, stuff happens in this annulus. This is work I did a long time ago, where it's also trying to make forecasts. The lead time is about this far as the arrow, and it's actually trying to forecast the forecast error, giving you an idea of the range of the forecast error, and trying to find model uncertainty. The parameters I'm worried about here, they're more like an empirical model in statistics or applied maths. I have a delay time, I have a reconstruction embedding, the size of the dimension, right? I have to figure out what functional forms or types of functional forms I'm going to use. Those are my parameters. Rollins' parameters aren't like that at all. His parameters are like the viscosity of water in a computer, how many modes to keep when he truncates Navier-Stokes. It's a very different kind of parameter estimating. And I think we'd do well to sort of contrast that better. But okay, let's ignore this. Let's talk about real forecast. So this is the current 3-month forecast for temperature in the UK. I think it's in the UK. Average UK temperature. And how do you do this? Well, typically, you take a model just like Rollins. Okay, Rollins, the annulus model was built by the Met Office. It had the same dynamical core 50 years ago. We take a sample of 51 members. We're going to do a Monte Carlo experiment in a 10 to the 7 dimensional space with 51 members, because that's all we can run before we have to call the BBC and tell them what the weather's going to be. Okay? So this is much smaller than this space. We move these forward in model land at model time. And for each member, we try to figure out what our target was. Our target here was a 3-month average temperature over the UK. And that's it, right? So I'll let you know. I will draw a line on this, and I'll send it to some working group when we actually know what the outcome was. How do we deal with something like that? Well, these are the simulations. These are the ensemble members projected back into the real world from model land. These are the observations going back a number on the previous slide, 25 years or so. These are the recent observations. This is sort of a known neglected. We believe, right, the people who run this model believe the Earth is warmed, and therefore this is no longer an unbiased sample of what next year's temperatures are going to be. We have these ensemble members. What do we do with them? Well, we're just going to do something really simple. We're going to take some kernels, right, little Gaussian kernels, and we're going to put a Gaussian kernel on every single one. We also have some background information from that climatology. Our ensemble is finite, and every once in a while we'll let something out here, right, or something inside. So we're going to find a blend. Well, so here we formed our forecast from the model. Here we have our climatological distribution, our prior, before we have any observations. We add them together and we get something like this. And what we need, oh, sorry, this is the climatology. I'm getting ahead of myself again. Okay, so this is the climatology. This is the forecast from the model. Even in weather forecasting, where we literally forecast 4 times a day, we have a real problem with forecast busts, forecast outcomes which have really low probability, that aren't weird, they just have low probability, and lucky strikes. I mean, sometimes the ensemble is close together, and that's exactly what happens. And if you start resampling, you realize these cause all kinds of biases in your evaluation. Now what we're going to do is we're going to take these two, we're just going to add them together. Alpha times our model PDF plus 1 minus alpha times the climatological PDF, and we get something like that. And then we see how alpha changes as we move out into the future. And we always see something pretty much like this. Alpha starts off, hopefully, relatively high. Maybe it doesn't always start out high. But if the model has information, alpha starts out high, and it decreases down towards 0. It'll never quite reach 0, even with a perfect model, but it'll reach something like the ratio of the number of members in your ensemble divided by the number of members in climatology. And by doing this and then evaluating it with a proper scoring rule, right, we build it with a proper scoring rule, we evaluate out of sample. Everything I show you is out of sample. we get something like this. And we just go back and we do this. But if I show you the results for this result, there's still only a handful of results. It's a relatively new product, right? And we only make 3 of these per year. So instead, I'm going to show you what happens if we go to the 10-day forecast. So the European Center for Medium-Range Weather Forecasting makes several of these 10-day forecasts. It makes one with a very high-resolution model, and it makes one with this ensemble model. And these guys are always fighting over CPU time and trying to see how much they are worth. And in this paper, we see we could plot this in log p-score over here. This is just a communications issue. It's plotted in relative interest rates. If this was betting against the climatology, it actually has really quite significant, a couple bits at the beginning, all the way out to day 10. This is the high-res model. If you just take one model and you dress it with your best, with a single kernel of any shape you can find, right? It decays actually more fast, and it in fact goes negative. It shouldn't go negative. We blended it so it wouldn't go negative, and this is an out-of-sample test. But also, we can let the high-res play against, right? Running casinos and weather forecasting centers is really, really popular. We can let the ensemble play against the high-res. It doesn't do so well in the first couple of days, but towards the end, it's really significantly better. Okay? And these are all bootstrap resampling range. So we're far, far away from 0. But we can't really get probabilities. Well, we could get probabilities, but when we try to evaluate those, I'll show that to you in a minute with the hurricane example. We have more information than the climatology, but the 10% events don't happen 10% of the time, right? So if you bet on ECMWF and you let me play against you, knowing nothing more than that your model is wrong, I will take money off of you. So maybe we don't want to give these to people who are making big decisions about life and property. There's still a lot of information in these forecasts. So this is a St. Jude storm from 2013. The data is from ECMWF, and we discussed it in our paper. And here's what really happened. Well, not quite, but these little dots, this is the maximum wind speed at all these stations all over the place. And this big low-pressure system, right, this is the storm. But this is inside the model. And these are measured in the real world. If I had a satellite photograph, it would be better, but I can't get one at the right time. This is the maximum observed over like 2 days, And this is at a particular snapshot of every 15 minutes or every 6 hours. They only archive every 6 hours. And this is a forecast. It's actually a pretty good forecast. How far in advance do you think we could have seen this storm coming? How many of you think we could have seen it the morning the storm happened? Raise your hand. If you're asleep, wake up and raise your hands. I'm going to ask you to take them down. 2 days. 4 days. 8 days. Yeah. Okay, let's see. So this is what the ensemble system actually looks like. This is the 51 members and the high res. This is forecasting the morning of the storm, 12 hours ahead, and they all have storms. And the high res has a more detailed storm. This is a day ahead, storms. That's 2 days ahead, storms. That's 4 days ahead. Well, they start to move around a little bit, but big storms. That's 8 days ahead. The Met Office does not have a warning system that goes beyond 5 days. It did not know what to do when they saw this. Right? That's 15 days. And if you look at, where'd they go? This guy and this guy, right? 15 days in advance. Now, I don't want to count these. Take 2, divide by 15. See, they don't even run the high res out that long. I don't want to count this. I don't want to take 2 divided by 51 and say that there's a 4% chance of having this storm happening. I really don't want to do that, right? But still, there's a huge amount of information here. How do we use that information in uncertainty quantification? As far as I know, nobody really knows. Or better even, how do we take this whole setup and use the setup to better inform the likelihood of a storm? This is really good. I checked, they're not always storms to 15 days. We can't evaluate a forecast like this anyway, because the return time of a storm this big in this particular place is, well, we've never seen one before, and I doubt anyone in the room will see one again. So we have to start making all sorts of reference class generalizations. But still, the forward simulation is good enough that neither model error nor chaos makes the ensemble of only 51 points useless. Okay. Here are the hurricanes. This is live. This is online now, or was online. Nothing's happening. I'll just note that here, the forecaster, Bevan, actually signs the forecast. This is pretty short because nothing's happening. Oh, also, no new tropical cyclones are expected. That only means that the probability is less than, well, they're not, some people say 10% and some people say 5. But none doesn't mean none. This is from last week or the week before. There's a lot more work because there's this thing up here that was sort of yellow and might turn into something. And it was 20% in 48 hours and 30% in 5 days. So if it's going to do it, it's probably going to do it now, but maybe it's going to do it later. The next day, it went up. Now it's 60% and 60%. So Brennan and Stewart are pretty sure that if it's going to go in the next day or two. Or are they, right? I can't get a clear interpretation from NHC about how to interpret these two numbers together. And it did. It turned into Ernesto. And then this other little yellow thing appeared down here. That's a 2020. Once it's turned, of course, the probability is over. And then nothing happened. That actually didn't happen. But what can I do? Well, Alex Jarman can go through all those graphs and collect all those probabilities and count the number of times that a 20% forecast in 2014 came through, and it looks like it's about 7. The chance of, if the probability really was 20%, the chance of getting 7 is about 1 in 1,000. So here it is on probability paper. These two ones are actually off the scale. So this is 1 in 1,000. The probability of being that low, if this probability was right, just resampling the actual probability to see the chance of getting this result was somewhere between 1 in 100 and 1 in 1,000. These are because I've looked at many bins, these are the correct, Bifernoni corrected over on the right. And I'm not well calibrated. So how's someone supposed to use this? I mean, that's an honest question. I mean, how do I'm doing, and in many, many, many applications, I used to say all, right? We go through this huge amount of work to do the manipulations right and get a PDF or a binary, trinary, a futile probability distribution, and then it isn't well calibrated, and then we blame the model. I mean, there are lots of things to do, but there's the question, how do we use this kind of information, or should we stop and try to go back and use that one we saw far in the future? This is so far this year. This is also very common. Almost always, the really high probability, really high, 70, 80, 90, they almost always change, and they almost always change within 24 hours. Right, so everything's down here. Everything looks quite reasonable in this case so far. This is the one I'm not supposed to talk about this, but I will. This, after literally years of looking for something I can't do the annulus. The annulus. I can't do an electric circuit and get well-calibrated probabilities. The NFL 538 has well-calibrated diagonal forecasts for the individual probability of a home team winning. This is by Ed. Ed also has another distinction. Of all my graduate students, he's the only one who's barred from 4 different casinos in the UK. Okay, so I think there are a number of these sorts of things that cause us challenges, and that somehow I would like to understand better at the end of this program than I understand now. One is ensemble estrangement. We may be in a huge dimensional space, but we can still look. With 51 members, I can look at a 50-dimensional subspace, right? With 3 members in 3D, I can look at a plane. Define a plane, right, and look at reality. Ensemble estrangement is when the plane does this and reality does that. Right? All these things about redoing your variance and doing stuff with your common, it doesn't really, it's not the fact, you can make it so that you can make these guys farther out so that the distance from these guys on average is the same as the distance from this guy to those guys, but you're doing it in the wrong subspace. What's another one? Initial distributions fail to reflect the model manifold. There are many ways of doing data assimilation, trying to get those observations into model land. Most of them ignore the structure of the equations. They structure the equations put on the distribution. It is not uniform. Most of our physics equations are dissipative in the sense that we will move towards lower dimensional manifolds, maybe attractors. Right? But if we look at what happens when we do a common filter, the common filter sort of moves around near the place, but it doesn't actually try to fall on that manifold at all. And sampling on a n-1 dimensional manifold in a 10 to the 7 space is a lot, saves you a lot. So how can we handle that? Indeterminate parameter values. When the model is structurally correct, we actually can put priors on the parameter values, and everything works, right? If we do something like add that c sine x over c term, it don't work no more, right? And it's because it doesn't even have, it's not a question of being imprecisely known. There are no values you can put in that structurally incorrect model that will reproduce the correct model. Big surprises are when things happen that we didn't think we expect. The Met Office on UQ I'll skip. And then just the relevance of discrepancy, which I will have plenty of time to get to. So this is one of the ways I want to try and quantify to make it easier for people to use models or decide that they don't want to. Very often, operational models are driven by long-standing, probably arbitrary statements. We will run to 2100. But what if the probability of the model being useless is over 99% in 20 years? We run to 2100. We will have 51 ensemble members. What else do we do? Things like that. Okay? So if you talk to the people who are running the models, who also have a lot of domain knowledge, you can ask them questions like, how long will it take before missing this 2-kilometer wall of rock has an effect on the Amazon? And the answer comes out to be only a couple years, right? I mean, water the physics, right? Air goes up, water falls out, water goes around. Air doesn't go up, water goes over the top. We had an insurance company in Norway interested in exactly the same question about snowfall under climate change given the mountain ridge that runs down Norway, Sweden. Norway has only 3 grid boxes in that model. There is no mountain range, right? But we can try to work out what would happen, right? What would happen in those kinds of situations if the Amazon if the rainfall in the Amazon changed a lot? How long would it take for it to change? This is the Okefenokee swamp. I highly recommend it. It's my favorite swamp. I grew up about there. There are no mosquitoes in this swamp. But if it stopped raining here and this turned to sand and was very white, how long would it take for that to happen? How long would that blotch take? Those feedbacks, how would they propagate? Would they be local? If the Amazon dies, that ain't going to be local. But what's the chance of that? Right? So in many ways, we can try to work out these kinds of things in the time scales and slowly increase our probability of a big surprise as we head out in lead time toward whatever lead time we're aiming at. And then we could actually think about stopping to run the models when the probability is too high. So while large model runners aren't interested in this, insurance companies and reinsurance companies are very interested in this. Right? So if I know I don't want to look at them, or if this was on a time scale of hours or days, start would be interested. If I know that I have no information on the phenomenon I'm worried about after here, I don't want to spend my time looking out here. I don't even want to see it because I don't want to anchor on bad information. So I'd argue no presentation of a model-based probability is complete without an expression of model irrelevance. What's the chance that for this particular PDF, for this particular target, my model is absolutely irrelevant? Irrelevant because my model can't do the things that are likely to happen, the things that have this probability of happening. And, known unknowns you can account for explicitly by sampling. Unknown unknowns we can't, but known neglecteds, right? So unknown unknowns, you sort of have a belly feeling. Known neglecteds, you have a really good feeling. Really good, because it's just physics. It's what physicists do. This is Reason Machete. He built a circuit to look like the Morse-Spiegel circuit. Eeks. To look like the Morse-Spiegel circuit. And what he's doing here, he's doing data simulation. This is voltage from one of these probes, model 1. He does data simulation over 32 samples, launches a 512-member ensemble. Looks really good until here, where the entire ensemble goes up, and reality turns around and goes back down. He then ran around 2 to the 20 more initial conditions. He cannot get this model to turn around. And it doesn't look weird compared to other things. This is a big surprise. The model just can't do that. He can actually go back and look, right, as they said this morning, once we've seen this, it's no longer, it's now data. It's no longer forecast. It's no longer out of sample. So having done that, he could sort of fix that. Model 2 actually does much better. Some of it turns around. He fixed around 26 of these before he got bored, realizing that in this space, he's just going to find more. Right? So there's a huge value of these kinds of empirical experiments. We have something like 100,000 years of weather data. Right? We can actually learn how things break and try to learn how to fix them. That's the ensembles. This is this issue of trying to estimate the parameters in a perfect and imperfect model. Yeah. But I want to move on to talk just a little bit about weather and climate again. So this is another famous picture. Oh yes, this one. This one has the, what is that? Is that a shark or a dolphin? It's really big. But, okay, so weather models, how far into the future, a weather model has asked, can I go before I have to turn something on? I want really high resolution. This problem with rainfall, I was actually in ECMWF when they went through one model version where the Alps got high enough that they would actually stop, they would actually cause flooding, high rainfall and flooding on the France-Italian border. And this is something we'd never been able to do before because the Alps were so low that all the moisture just went over them. Right? In one model revision, the Alps got higher. I have to remember not to say Andes. Right? Got higher, water hit, and of course it was at the wrong time and at the wrong place, but at least it was raining. Right? And so they would really like to leave as many things turned off as they can. But as it is, they have to turn on ocean waves. So they have a great wave model, which allows us to predict things for offshore platforms. They don't do this for the waves, but the waves change the drag of the atmosphere on the surface of the ocean. So they need that. And then there's this balance, right? The fewer the processes, the higher the fidelity we can put in the other ones, and we can change the way we distribute CPU time. But we don't really have all this in there. Oh, what do I mean by in there? Well, so first of all, this is a climate. And this says includes. By in there, I mean, this is a reindeer. It doesn't look like one, but it is. We can stick in a 2 lines of code reindeer model and say we have included reindeer. Right? But to simulate realistically or adequately or with something like reasonable validation is good. So sea ice. Do we want to put in sea ice? There was some sea ice. There is sea ice. Well, we only really want to put in sea ice if it moves or if it melts. And so this is the sort of thing. We turn on slower processes, lower and lower, slower and slower. If we're forecasting for wind generation in the next 24 hours, we turn off almost all of this stuff, right? And look more carefully at what the model says for wind generation. But a climate modeler, they just have a different, a climate model should be a more complicated weather model, right? To forecast the climate well, we need to include all the things that might have feedbacks that would change the climate at time in the future. But technically, what a climate model is what do we have to turn off in order to get our model to run to 2100, right? So that's the way we have to go. I mean, how do we can accept that, but then we need to think about how we're actually going to interpret those models, right? And I think this is the sort of thing that is very popular to talk about at climate meetings, but never really gets written up. Okay, can we see this coming? Yes, so this is actually the output of our climate models from the AR5, the most recent IPCC report. This is the temperature anomaly. This is actually how I met Jim, I think. We were arguing about an earlier version of this picture where everything was yellow for like 8 hours. Because this isn't temperature, right? This is temperature anomaly. This is if you take the average over these 20 years or so, and you subtract that, then all these models have to agree on average over this period, and you get this result. This number over here, which used to be hard to find, these are the numbers you have to subtract off. In other words, the model of this color, actually, that wiggly line has a mean of 13 degrees. If you plot the temperature, the actual temperature, the thing that goes into sigma t to the 4th, the Boltzmann law, they look like that. Right? So these are the same CMIP5 climate model runs, right, on the same scale, on roughly the same scale, and they're just very, very different. And so we can shrink them all down, completely violating all the laws of physics we use to justify running them in the first place. Okay? And then we can do statistics on them. But if we're making changes that are larger than what we expect in the system, how do we interpret the statistics on those anomalies? Okay, they're getting much better. Now I just want to talk about discrepancy and then another way forward. So in the paper with Jim, on page 4, we define discrepancy like everybody else. This is, except we have these, we have the real process on x minus the real process on y. And my difficulty is with this minus sign. Right? It's a question of how things actually work in model land and in the real world. Now, Jim says he hasn't worried about the real world much because he hasn't worried about leaving model land much because he doesn't have to do it. And there's a sense in which if you're building empirical models, you really don't. I mean, you're in the real world and the model world are measured in terms of those observables. But that's not the case in these large simulation models. And we go on to say later that could cause problems. I just wanted to give a simple example. So I want a really good model that's really easy to understand, right? And so what I'm going to do is I'm going to take these equations as my system, and I'm going to take these equations as my model. Except I'm going to run these in double precision for my system, then I'm going to run them in single precision for the model. Right? So that's a good system. I think the same sort of thing happens. It's literally the same code. It's the same machine. And if I iterate it ahead 24 stops, this is the discrepancy, the system minus the model defined with initial conditions in the system space. And this is small. This range is about half the diameter of the whole range of the dynamical system. And what I'm showing you is the distance between the 2 points that started as close to the double precision point as the single precision model could. But by 32, I'm starting to get this weird structure, and I have points that are as far away as they can be. And at 48, I effectively have some random, potentially fractal structure. This is the actual, never mind. This structure, the discrepancy is extraordinarily complex and a very simple nonlinear two-dimensional model. Right? And in terms of, so it's hard to relate this one back to the atmosphere, but this is not asking for something completely crazy. So what this is saying is that the discrepancy has this kind of structure. And that structure, well, it doesn't really, because that's impossible. This is, I'm zooming in now, so I've zoomed in by a factor of 3, and I can see the single precision grid. So what am I doing? All these points I take the double precision, so I'm now using state space for the model state space. So all the values inside one of these squares for double precision is the single precision value. And now I can actually see that at the grid level for single precision, right? I don't have anything smooth. And this is going to cause detail problems. I think there are other issues about ignoring subspaces that we talked about some time ago. And now I can go to one more thing. I don't know if you know this one from Alice or anyone. Sometimes I believed as many as 6 impossible things before breakfast. This, Alice says she can't, and the Queen says she just has to try harder. Simulation modeling in the environmental sciences is a good way to believe things that are impossible. So here's Jim doing his paper on Montserrat, and they use a model to build some hazard maps for Montserrat. After time goes by, they've got too many 1 in 10,000 year events. Jim is not as old as he looks. He shouldn't have any of these, I don't think. So they look for a flaw, and they find a flaw. There's a poorly estimated parameter value. So they build new maps. And so the question I always love to ask them is, are they right now? How much confidence do you have in the new maps? Right? Was that the only problem? Did you find the last bug? I'm astounded at the number of large-scale modelers who will say yes, in my part of the code. In my part, or they either think their part of the code is the worst part of the whole model, or their part of the code is the best part. And maybe we could just try, how do we find a way of embracing the fact that there's going to be a bug, right? There are going to be things that we don't know. We aren't going to get viscosity exactly right. We don't know exactly how big the eruption will be, but can we give some kind of probability of a big surprise on what happens? This is Joost van Hardenberg. We were up looking at ibis in the Alps, same model as the reindeer. They came down for breakfast. They said, 3 bugs before breakfast. This was in one of the best existing climate models in the world, right? And he'd find 3 bugs in his hotel room before breakfast. And they weren't trivial bugs. They were things like, they were fundamental physics bugs, which I'm happy to talk about later. And this is just going to be the case. I think we focus too much on how we would analyze a perfect model. We miss the dominant relevant uncertainties, right? The things that are actually going to cause uncertainties in practice. So how do we get this kind of information? Well, you remember there are a couple of good ones over here. Well, what if we saw this guy at day 15, and instead of just running the system again tomorrow, what if we ran a bunch more ensembles near that initial condition? What if we tried to figure out how the model managed to get from where it was today to this storm? And what if every day as we got closer and closer, we kept focusing to see, has the model now moved so far? We already have this nice trajectory of our model. Has the model moved so far away? Have the observations we made in the meantime made this less probable or more probable without actually knowing how probable it is, ever? And doing this, we could find interesting information for a number of practitioners and users of these practitioners. Insurance companies would love this. They don't need to know the probability. They just need an idea. They need a better idea. There's many different ways that we could potentially, you could design nuclear power plants in a different way. Right now, nuclear power plants in some countries are treated, weather is treated like earthquakes. You assume it happens with no warning at all, right? And that's good. They're always risk averse. But you can turn off a modern nuclear power plant in about 2.5 days. So if you could show them that no giant storm, almost no giant storm, could appear in less than 4 or 5 days without warning, the potential, well, you do a calculation. Hey, look, if I can build a plant and put, assuming I can find a place to put them, I can build 3 for the price of 1, and chances of me having to turn them all off at the same day is completely unknown, but it seems like it ought to be small. Right? So we can actually do things better with this kind of glimpse methodology. And still, as a physicist, I mean, it's just really hard. When you look at things like this, this is the Canary Islands, this is vortex shedding, these kinds, you can hexagons, right? This is, G.I. Taylor, who wasn't read into the atomic bomb, calculated the strength of the atomic bomb by applying scaling laws to a series of propaganda pictures the US Army put out. They were not happy. But how does it work? I mean, there is this sort of miracle that it works at all, that physics works at all. But it does. But it doesn't work precisely mathematically. If you start looking carefully enough, you start seeing deviations all over the place. And given that we're going to die before the physics-based models of interest include these length scales at all, right, much less those phenomena, how can we actually use those facts? Can we actually do something different than just trying to pull probability distributions out of our models? Thank you very much.